You started it?
Yes.
Good, thank you, Gavin.
Oh, really?
Yeah.
Okay, great.
Doesn't pay attention.
All right. Hey, guys. Yesterday we learned about resistors in a series. Now we're going to learn about resistors in parallel. We're going to see what parallel wiring is, and we're going to see how to get the equivalent resistance of a bunch of resistors in parallel, and it will be fun. Here we go. Resistors in parallel. Alrighty, first, parallel wiring. I've got to define what parallel wiring is, but just like yesterday, I need to define parallel wiring in terms of electrical thinking. I can't define it in terms of what the resistors look like. Like yesterday, you'll notice I didn't define series resistance, series wiring as just hook them up end to end. Because I can show you resistors that appear to be hooked up end to end, but they're actually not in series with each other. You see what I mean? And it's the same thing with parallel wiring. Just because two resistors look parallel doesn't mean they are parallel. Parallel wiring has a very specific definition, and I'm going to give it to you now. Okay? Devices are connected so that they all have the same voltage. They all have the same voltage. And I'm going to say voltage drop because that's actually or voltage difference. Let's say voltage difference. But if you want to just think in terms of the same voltage, that's fine. But they all have the same voltage difference. That's what parallel wiring is. You're looking at the voltages. If they all have the same voltage, then they're wired in parallel. Let me give you an example. Suppose I had a 12-volt battery, and I had this resistor, R1, wired like this, and this second resistor, R2, wired like that. Are these resistors in parallel with each other? Are they in parallel with this 12-volt battery? Well, they look parallel, right? Because, they look parallel. But to answer the question, I have to answer, do they have the same voltage difference? Or in the case of resistors, voltage drop. I'd like you to see, because this side of the battery is hooked up to the 12-volt battery. This side of the resistor is hooked up to the 12-volt battery, the positive terminal, which is at 12 volts. Then he's got 12 volts there. Because this side of the battery is hooked up to the negative terminal, which is 0 volts, he has 0 volts there. This side of the resistor is attached to the 12-volt battery, so that's at 12 volts. This side of the resistor is attached to the negative terminal, so that's 0 volts. So I want you to see that R1 and R2 are indeed in parallel with each other, because they both have the same voltage drop, 12 volts. And in fact, they're hooked up in parallel with the battery because they all have the same voltage drop as the battery, or voltage difference as the battery. Before I go on, there's something I need to tell you about conductors with these electrical circuits that I've never come right out and told you, and that's this. Every point on a conductor has the same voltage. We're assuming that this conductor is presenting no impediment to the flow of charge. We're assuming that this conductor has no resistance. So that if I had some conductor like this, and I told you, hey, the voltage right there is at 12 volts, well, because there's no resistance to the flow of charge, there's no resistance, this point is 12 volts, this point is 12 volts, this point is 12 volts. Every point on the conductor will also be at 12 volts. Because if charge moves from here to here, there's nothing to impede the flow of charge. So whatever energy the charge has here, it'll have that same amount of energy here, have the same amount of energy there, and so on. If I can say this in words, it would be to say all points on a conductor are at the same voltage or the same electrical potential. And so let me write that down. All points on a conductor, and this is a perfect conductor. This is a conductor with no resistance. All points are on a conductor are at the same voltage. Okay. I'm going to hook up a third resistor, and I'm going to ask you to tell me if it's in parallel. Here comes the third resistor, R3. Is R3 in parallel with the voltage source and R1 and R2? Doesn't look parallel. How many people say R3 is indeed in parallel with everything else? Okay. How many people say it's not? Okay, great. Cole, how did you know that it was indeed in parallel?
Well, because it connects the battery to the R3 and then it ends right there at 0 volts. It's in a loop.
Beautiful. You guys okay with that? Even though it doesn't look parallel, it is, right? Because the voltage drop across it is the same as everybody else. 12 volts there, this point is 0 volts, this point is 0 volts, that point is 0 volts, and then, yeah. Okay, so it is in parallel. Now, if any of you become electrical engineers and you start drawing circuits and you have a bunch of resistors in parallel, you're not doing anyone any favors by not drawing it looking like parallel. You'll just fake people out. You'll encourage mistakes. So definitely when I was drawing circuits, if I had something in parallel, I always drew it in parallel, you know, so that the world would know, hey, it's in parallel, you know. But to decide, make that decision as it's in parallel, you're going to have to ask yourself, does it have the same voltage? Let me give you another circuit instead of R3. How about this? Here's R4 and here's R5. Is R4 in parallel with R3 and in parallel with the 12 volt and R1 and R2? It looks parallel, look. How many people say R4 is indeed parallel to R3? Okay, great. Does anyone say R4 is not in parallel? Hey, good for you guys. Tell me, what's preventing R4 from being in parallel with R3? Yes, Noel? Yeah, R5, the presence of R5, right? R4 can't have the same voltage drop across it as R3 because the voltage here is 12 volts, but is that voltage 0 volts? No, that voltage is 0 volts. And if current is going through these resistors, there's a voltage drop across R5. That's not going to be 0 volts. You see? Yes?
If the voltage drop of R4 and R5 are the same, would they be in parallel wiring?
No. No. So you're right. I mean, you know, yeah, no. So I don't know how to say that. They're connected so that they always have the same voltage difference, and they also have to be connected. Well, let me elaborate on what you said, okay? Let's say we wanted to connect me and Earl in parallel, okay? If we're going to connect me and Earl in parallel, then unlike yesterday, remember when we did Kumbaya, where I have the one student's right hand clasped in my left and another different student's left hand clasped in my right, and we all went around and that was series wiring? Well, parallel wiring, if I'm going to be parallel with Earl, then my left hand has to grasp his right hand, and my right hand has to grasp his left hand. And we have to be connected in that way. Okay, and then at that point, we can start dancing or doing whatever, but we have to be holding hands, right? So they can't be parallel unless somehow this guy's hand is holding that guy's hand, because they need to be holding both their hands. So to be parallel, both sides of one resistor has to be holding both sides of the other resistor. So you're right, even though you get this special situation where two resistors in series with identical resistances, meaning they're always going to get the same current, so they'll always have the same voltage drop across them, but they're not wired in parallel. So I guess I should have elaborated on this. Devices are connected so that they all have same voltage difference, and they hold both hands, both of each other's hands. Okay? So let's say me and Earl are in parallel. We're holding each other's hands. Let's say a third student wanted to be in parallel with us. How would that work? Where would they have to stand? How could a third student be in parallel with me and Earl? Yeah, Earl?
They have to hold both our hands.
Cool. So where would you like him to stand?
Below us.
Okay, in between us and below us. Good. Great. Or maybe behind Earl, right? And now you'd have three of us in parallel. I'm holding Earl's left hand with my right hand and Earl's right hand with my left hand, but also the other person's, left hand in my right hand and right hand on my left side, right? And if a fourth person wanted to be a parallel, we could put him behind me. Now it'd be a little more difficult because I'm a lot fatter, but they would still somehow want to reach around and then be grasping our hands, right? And each parallel resistance, you're going to have to put them behind us or maybe below or above, who can say, as long as both of their hands are clasping both of our hands, right? So tell me, R4, his left hand is clasping this guy's right hand, but who's R4 with his right hand? Whose hand is he clasping? R5. So R5 is like an interloper, It'd be like if someone came to me and Earl and they clasped one of our hands with one of his hand, but his other hand clasped someone else. Well, he's not in parallel, because you got to clasp both of our hands to be in parallel with us. So yeah, thank you, Earl. That's a really good point. I was I was so into making sure you understand that they have the same voltage that I forgot to say, oh, and by the way, they're holding each other's hands. Yeah. Oh, so silly me. Hey, let's go further. Let's do the math. Here comes the math of parallel resistance. Draw a circuit, but keep a lot of space above, because we're going to add additional resistors. So I've got a 30 ohm resistor, and I've got a 12 volt battery. And like I said, if you draw this, leave some space above. How much current is this battery delivering? How much current is coming out of this battery? How do I figure that out? Good, V equals IR. 12 equals I times 30. So 12 over 30 is the I, and that's 0.4 amps, right? So this battery is delivering 0.4 amps. That 0.4 amps is coming up here and then ending up over here. And that 0.4 amps multiplied by the 30 ohms, I get a voltage drop of 12 volts. 0.4 amps times 30 ohms, 12 volts. So you see, these two guys are in parallel because he's getting the same voltage drop as he is. Okay? I am now going to attach another 30 ohm resistor in parallel. Okay? Because this 30 ohm resistor is in parallel with this one, he has to have a 12 volt drop across himself. 12 volts. And so tell me, how much current must be entering this 30 ohm resistor? 0.4 amps, just like the other one. So here comes my next question. How much current is coming out of the battery? He has to deliver 0.4 amps for this guy and 0.4 amps for that guy. How many people are thinking 0.8 amps are now coming out of the battery? Okay, good. You guys okay with that? This battery is now delivering 0.8 amps. So, he's a 12-volt battery. He's delivering 0.8 amps of current. Let's go ahead and get the equivalent resistance he sees. V equals I times the equivalent resistance that that battery sees. He's a 12-volt battery. He's delivering 0.8 amps. The equivalent resistance he sees is 15 ohms. Essentially, by adding that additional 30 ohm resistor in parallel, I've reduced the resistance that the battery sees. Another way to write this would be to say a 30 ohm resistor in parallel with another 30 ohm resistor gets me 15 ohms. Do you see that this is different from series resistance? Series resistance, each resistor you add just increases the resistance. You're making that gauntlet you have to travel through longer and longer, okay? But parallel resistance, I add a parallel resistance, I've reduced the equivalent resistance. Does anyone have an idea why? Why is it that adding a resistor in parallel would reduce the equivalent resistance to the flow of charge? Yes?
It causes the battery to give more power.
Okay, it forces the battery to provide more current, to provide more power. Good. Hey, let me give you an analogy. Imagine I've got this big swimming pool, okay? This swimming pool that's filled with water. That's like my battery. This battery has a bunch of charge held captive by the battery, just as a swimming pool holds a bunch of water captive. But when I put this 30 ohm resistor across this battery, it's like punching a hole in the swimming pool, and now a bunch of water is flowing out. Tell me, what does it mean if I put another 30 ohm resistor across that battery in parallel with the battery? What am I doing to my swimming pool?
Adding another hole.
Yeah, I'm adding another hole, right?
Oh, it's crying.
I'm making, boo. Okay. Yeah. By adding a resistor in parallel, I'm providing another pathway for current to flow out of the battery. I'm punching another hole in my swimming pool. Here, let's add a third resistor. Let's add another 30 ohm resistor. Well, he's in parallel, so he's going to need that 12 volt drop. And to get that 12 volt drop, he's going to need 0.4 amps. So now the battery isn't putting out 0.8 amps, he's putting out 1.2 amps, right? 0.4, 0.4, 0.4. Three 30 ohm resistors in parallel requires 1.2 amps. You tell me, what equivalent resistance is the battery seeing now? Yeah, you guys get that? 10 ohms, 12 volts, 1.2 amps, V equals IR. I'm hoping you see that a 30 ohm in parallel with a 30 ohm that's in parallel with a third 30 ohm gets me 10 ohms. Each additional resistor I add makes it easier for charge to flow out of the battery. Hey, you tell me, someone who's good at inductive reasoning, what if I have 4 30 ohm resistors, just a second, in parallel? What's that equivalent resistance going to be? 5 ohms? No, sorry. Tell me, what's it going to be?
7.5.
How'd you get 7.5?
30 divided by 4.
30 divided by 4. Do you see that? 30 divided by 2, 30 divided by 3, 30 divided by 4. Tell me, Chris said 5 ohms. How many of these resistors in parallel would I need to have in order for me to get equivalent of 5 ohms? Yeah, thank you very much, 6. So I want you to see that generally, n identical resistors of value R in parallel has equivalent resistance EQ, or maybe I tend to use small e small q equal R over N. That's simple. But what if the resistors aren't identical? Well, then we're going to have a formula for equivalent parallel resistance when they're not in parallel. And I'm going to, derive that right now. And then I'll do a problem, and I'll have you guys do a problem, then we'll be done. But all of this stuff is just to try to get you to understand conceptually what's going on. The parallel resistance formula. Okay, I'm now going to derive the parallel resistance formula, and you don't have to write this down if you don't want to, because the only thing that matters is going to be the formula that I end up with. Okay, so here, suppose I had this situation. I have a resistor R1, a resistor R2 in parallel with a battery V, and you don't have to write this down. Okay? And suppose this battery V is putting out a current I, and then that current is being split into these 2 tributaries. One of the tributaries a current I2, the other guy a current I1. Oops. Current I1. And I hope you see that I have a relationship between I1, I2, and I, the current out of the battery. And that relationship is I equals I1 plus I2. But here's the thing. The voltage drop across this battery is V, or the voltage rise going right to left is V. And so the voltage drop across here is V, and the voltage drop across there is V. Which means I can do Ohm's law. I can go V equals I1 R1, and I can do V equals I2 R2, and then I could solve for I. So I1 is V over R1. So here we go. I1 is V over R1. I2 is V over R2. And I'm going to factor V out. And then I'm going to divide both sides by that thing so I can get V. And guess what? That's the equivalent resistance of 2 resistors in parallel. It's the reciprocal of the sum of the reciprocals. That is, if you want to look at it like this, V equals I times 1 over R1 plus 1 over R2 to the negative 1 power. Then that's the equivalent resistance. What if I've had a third resistor in parallel? What if I had this guy, R3, okay? Well then, I'd have another current, R3. I'd have plus I3, and so I would have V over R3, and then this would be 1 over R3, and so this would be 1 over R3. And however many resistors I have in parallel, I just add more terms. And so generally, the equivalent parallel resistance, which I'm going to write as R sub parallel. I'm going to put 2 little parallel lines. I think our textbook calls it R sub P for parallel, but however you want to say it, the equivalent parallel resistance is 1 over R1 plus 1 over R2 plus 1 over R3 plus dot, 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 all to the negative 1 power. And that's the formula you're going to have to memorize for the equivalent resistance of a bunch of parallel resistors. It is now time for me to do a problem. And then you guys. Here comes example number 1. Okay, let's say this is 10 ohms, this is 30 ohms, and this is 12 volts. Go ahead and write that little schematic. I'm going to ask for 4 things. Number 1, I want the equivalent resistance that the battery sees. Number 2, I want the current that's coming out of the battery. Number 3, I want the current going through the 30 ohm resistor. And number 4, I want the current going through the 10 ohm resistor. Okay, here we go. I'm going to do this problem. First, the equivalent resistance is 1 over 10 plus 1 over 30 to the negative 1 power. And when I do the punchy in my calculator, I get 7.5 ohms. If I may recommend, if you have a TI-83 or TI-84 or an N-Spire even, I would do it like this. I'd punch parentheses, and then I'd punch 1, and then I'd punch 0, and then I'd punch the x to the negative 1 key, and then I'd punch plus, and then 30, and then the x to the negative 1 key, and then end parentheses, end parentheses, and then the x to the negative 1 key. That, to me, is the most efficient way to do the punchy on the calculator. Just use the x to the negative 1 key repeatedly, instead of using fractions. Okay? The current out of the battery, V equals IR, so I got V over R is going to be the current out of the battery. My 12-volt battery sees 7.5 volts. And so this ends up becoming 1.6 amps. The current through the 30 ohm resistor, well, this is a 12-volt drop, right? Both of them have to have 12-volt drops. So I got 12-volt drop, 30 ohms of resistance. That's 0.4 amps. This is a 12-volt drop as well. 12 volts divided by 10 ohms is, 12 volts over 10 ohms is 1.2 amps. Someone tell me, why did of this 1.6 amps that's coming out of the battery, why did the 10 ohm resistor get the lion's share of the current? Why does he get 1.2 amps and he only gets 0.4 amps?
Less resistance.
What's that?
Less resistance.
Yeah, less resistance, right? You've got a river of current and he's got 2 paths to choose. The path of least resistance and the path of lots of resistance. Well, this is the way you should live your life. Always choose the path of least resistance. That's what current does. If it's good enough for current, it's good enough for me, right? I'm married. How did I get married? Did I search for the right woman? No, I just waited for someone to choose me. Path of least resistance, and guess what? I'm happy as heck. Okay? I recommend that. Why am I a teacher? I got a master's degree in engineering. I was looking for jobs in engineering. Why am I a teacher? Because my friend, who's a teacher here, called and said, "Hey, Larry, we need a calculus teacher." I said, "Great." And I'm here. And guess what? I'm happy as heck. So I totally recommend path of least resistance. If that's all you ever follow, you'll be so happy. Okay. You guys ready to do a problem on your own?
Interesting.
Darn straight, man. Okay, here we go.
I like it.
Okay. Okay, I've got a, whoops. What have I got? Just a second, I forget what I wanted you to do. Yeah, okay, that's what I want you to do. This is a 5 ohm resistor, this is a 20 ohm resistor, this is a 20 volt battery. Please get me the equivalent resistance, get me the current out of the battery, get me the current in the 20 ohm resistor, and get me the current in the 5 ohm resistor. Good luck. I'll give you like 2 minutes to do this, because it's just so fast.
You need a calculator.
Is anyone having difficulty getting started?
You punched me first.
Yeah. I wonder if the sound will catch that.
It does.
And you'll have video evidence that when he hit you, it went hit, and then when you hit him back, it went poof. So we'll know. Okay, how many people got 4 ohms for the equivalent resistance? Yay. Okay, then the current out of the battery, 20 volt battery, 4 ohms. He doesn't see 5 and 20. He sees 4. He sees the equivalent resistance. So I hope you guys got 5 amps. How many people got 5 amps?
Yeah.
Okay, yay for you guys. Any questions so far? Okay, then let's go ahead and get the current between the individual resistors. Okay, 20 volts, 20 ohms. Hope you guys got 1 amp. 20 volts, 5 ohms, 4 amps. There's a couple of things I want you to notice. First of all, what do you notice about the ratio of the resistances and the ratio of the currents? Okay, but I mean, I'm talking about the ratio, like 20 to 5, 1 to 4. What do you notice about those ratios? Good, they're the same except inverses. Good, because the big resistor has to get the small current, path of least resistance, you know. So you guys okay with that? This is called a current divider. And when you have a current divider like this, whatever the ratio of the resistances are, the reciprocal of that is the ratio of the currents. There's another thing I want you to notice. Do you notice that the smallest resistance here is 5? But the equivalent resistance was 4, it was smaller than the smallest resistor. Is that always going to be true for parallel resistance? Is the equivalent resistance always going to be smaller than the smaller of the 2 resistors? Hey, absolutely, because right now the resistance is 5 if the 20 ohm is gone. If I add the 20 ohm, will that ever increase the resistance? No way, and punching another hole in that pool is not going to increase the resistance to the flow of charge. So let me ask you this final question. I have 3 resistors in parallel, okay? I have a 30 ohm, a 20 ohm, and a 10 ohm. The equivalent resistance, what has to be true about the equivalent resistance?
That's less than 10.
Good, less than 10. The equivalent resistance has to be less than the smallest resistor in a bunch of parallel resistors. Okay, it's gotta be less than the smallest one, okay? Because again, if all you had was the 10, that's your resistance. Adding resistors, no matter what their value, adding resistors in parallel always reduces resistance. All right, hey kids, good luck on tonight's homework. And at this point I say bye-bye.